Hi everyone, I'm Arda, and today I'm going to be presenting the paper titled Cognitive Map Formation Through Haptic and Visual Exploration of Tactile City-like Maps from Otting and colleagues, published in the Nature Journal in 2021. The research asks, can people form an accurate cognitive map of a small city-like layout by exploring a tactile map by touch alone? And how does this compare to learning with vision? They had 18 sighted participants, half being in the haptic group denoted with H, that learned maps solely by touch, and the other half being in the visual haptic group denoted with VH, who used vision and touch together. All participants used the right index finger for exploration, and they learned 3 small Lego city maps in panel A. We see these 3 tactile maps on top view, and the items, the 5 item locations, are shown on each map with striped rectangles. In panel B, we see an example of map A including the placement of the items, and all 15 items that were used in the study can be seen here in panel C. 4 tasks were done. After participants learned the maps, they estimated Euclidean and path distances between item pairs. They rebuilt the map, they placed the items on the map, and navigated the shortest route between 2 items in this order. Now, let's take a look at the results using the provided figures here. Starting off with the distance estimation task. This figure shows how accurately participants judged distances between items after learning each map. The x-axis lists the 3 maps respectively, and that stands for every figure in the results. For each map, we see 2 colored bars representing error in estimating Euclidean distance versus path distance. The y-axis is a normalized error score, with 0 meaning a perfect estimate error. Panel A is the H group and panel B is the VH group. And we can see both the haptic and visual haptic group had very low error scores on all maps, and we see that errors are small for both Euclidean and path distances in all conditions, so there were no significant differences between the 2 groups on any map. Moving on to the map reconstruction task, figure 5 shows how well participants could reconstruct the map layout. The figure shows the canonical organization score, which is a measurement of how well the overall layout structure was reproduced. On map A, both groups achieved a very high canonical organization score, which is near perfect, but on more complex maps B and C, the haptic only group drops performance to around 0.5. In short, VH group outperformed H group on medium complex maps, with significantly higher accuracy on map B and C. Continuing with the item placement task, this figure shows how accurately participants place the items back onto the map after learning. When we look at the figure, we actually see a trend of the H group having more error as the complexity increases, and the VH group dropping errors as the complexity increases. However, VH was better than H with statistical significance only on the most complex map, and the other differences we see here are not statistically significant. In conclusion, sighted learners formed accurate cognitive maps of simple Lego tactile environments with or without vision, and adding vision only provided modest advantage when maps became complex. It should be considered, however, the scale of a tactile map is close to a map drawing here, while the environment is experienced on a much larger scale when we are walking and experiencing the world. Although this study used a small and relatively simple Lego-based environment, the findings suggest that the advantage may be even greater in complex, dynamic, and large-scale environments we navigate through daily. Touch alone allowed participants to learn simpler layouts well, but as complexity increased, performance dropped without visual support, highlighting how multisensory integration can strengthen spatial memory, orientation, and route planning. So, in real world terms, this means individuals with visual or sensory deficits may face greater navigational challenges, while strategies such as tactile maps, auditory cues, and multimodal navigation tools could support their mobility. Thank you.